Hello everyone. In this lesson we're going to be learning about vectors. This is just an introduction. Some of you in some of your other classes may have gone over some of these topics. That's okay. We're going to go over these objectives. We're going to define what a vector is. We're going to discuss what equivalent vectors are. We're going to determine the component form of a vector, find its magnitude, and then graph. Many quantities in geometry and physics, things such as area, time, or temperature, can be represented by a single real number. Other quantities, on the other hand, such as force or velocity, involve both magnitude and direction and cannot be characterized by a single number. To represent this number, you would use a vector. And so when we talk about a vector, the definition of a vector, we are talking about a directed line segment that has both magnitude and direction. What this looks like is an arrow with an initial point that we'll call P and a terminal point that we'll call Q. And so in the notation, you would say that this vector PQ would look like that. Another way that you can label a vector is to just call it one letter. So I would say vector V is the directed line segment, PQ. The magnitude of the directed line segment, PQ, is denoted by this notation. And it's found by using the distance formula. And we'll cover that in a minute. The direction of the vector is going to be found by finding its slope, and we will look at that in a little bit later. A vector in standard position is a vector with its initial point on the origin and then directed in some direction. All right, so this one here is in standard position. This vector, and you can't hardly see it, but its arrow is here, is in standard position. This one right here is not in standard position. And the only thing that makes it in standard position is putting its initial on the origin. So when you're given an initial and a terminal point, P and Q, like we did before, you would take the terminal point, the terminal, minus the initial, and that would equal a vector in component form. That's an E. And that's denoted with those brackets. So 4, 3 would be a vector whose initial point is the origin and the terminal point is 4, 3. So in order to graph this, I would go over 4, up 3, just like you would do for a regular point. Start at the origin, end at the 4, 3, but put an arrow there. So that is a vector in standard form. To do this, I would do negative 3 halves, negative 2. So 3 halves would be 1 1/2, which is here, and then negative 2 here. So this one, as you can see, has a different magnitude and a different direction, pointing in a different way. So to find the component form of a vector, you would take the terminal point and subtract from it the initial point. In other words, using P and Q, I would do Q minus P. So if I'm going to do that, I would have Q, this is Q, 5, 5, minus P, which is 2, 1, and then I would subtract the x components, which would get me 3, and I would subtract the y components, which would give me 4, and that would be the component form of a vector. Okay, to find this one over here, we're going to do Q, which, and you'll notice that when it's in not in component form, they just use the parentheses and subtract. So I do terminal minus initial. So this is going to be 1 minus a negative 4, which is 5. Negative 3 minus 1 is negative 4. And the component form of that vector is 5, negative 4. So if I were going to graph this point, what you would find is that we had one very similar to that on the previous page, but I would put a point here, and that's its vector. Okay. To find the magnitude of a vector, you can see here I put a whole bunch of notation on here. But some of this you should recognize. You see the initial point, the terminal point, right? Initial, terminal point. And so to write the vector v, you would do terminal minus initial, or put it in component form. So this is just writing it out. The length of v is to find its magnitude, right? And the magnitude is the distance formula. So find and draw the vector v with an initial point p and terminal point q, and find the magnitude of v. So really all that says, find and draw vector v. So you would just draw these points. 1, 2, 3, 4, 5, 1, 2, here's this point, this is P. And then Q is at negative 4, 4. So here, that's Q, and so you would have this vector right here. To put that in component form, right, PQ in component form, V, would be terminal minus initial. So this is going to be negative 4 plus 5 for the x-coordinate, and then this is going to be 4 plus 2 for the y-coordinate. So in component form, it's going to be 1, 6. Right? So if I take this and move, it will be over 1, up 6, right? So it will look like this. So moving that vector over into standard position puts it in component form. Now, the advantage of putting that in component form is that now when you go to find the magnitude of v, you already have x minus x and y minus y. Can you hear the clock going off in the background? Okay, I've changed venues. All right, to find the magnitude of this, we have already done part of the work. So that when you go to find the magnitude of this, you have already found x minus x when you've put it in component form. So I can just do 1 squared and then 6 squared, which is going to be the square root of 37, and that's the magnitude. So I don't have to reinvent the wheel if I put it in component form, because if you'll notice, this was x minus x, this is y minus y, and that's what you put in the distance formula. Okay, so it's already done for you to put it in component form. All right, so that's the magnitude or the length of it. The direction of that is usually defined by a direction angle, and we'll cover that in later lessons. Equivalent vectors have the same magnitude and direction. And I'm going to cover a couple of different ways to determine if two vectors are equivalent. In order to be equivalent, obviously they have to have the same, they have to be the same length, and they have to point in the same direction. So if you're given two vectors, u and v, with the initial point at P and the terminal point at Q, one way to determine if these two vectors, looking at them by inspection, you can't tell, but one way to find and prove that they are equivalent is to find the slope of each vector and the length of it using the distance formula and determine if those are the same. All right? I'm going to let you in on a secret. These two vectors are not equivalent. And I'm going to show that by finding the slope between these. So you want to find the slope of u, the u vector, right, which is going to be y minus y over x minus x, which is going to be 1 over negative 3. Okay. The slope of the v vector would be 2 minus 3. That's the y minus y over 1 minus 2, which is negative 1 over negative 1, which is 1, and those are not equivalent. So these two vectors fail on the slope, and this shows it. They do not have the same slope, they are not equivalent. I would not need to find the distance, but if I did the slopes and they were the same, then I would go ahead and find the distance, and the distance is just finding the magnitude of the vector. So I would do negative 4 plus 1 squared plus negative 1 plus 2 squared. And notice that I'm just using the slope because I've already done the subtraction. This would be negative 3 squared plus 1 squared, which is square root of 10, right? So that was the magnitude. Now, I could do the same thing for v. The second method, though, is a little more straightforward and probably what we would do, and that's to put it in component form. All right, so if you do that, the u vector in component form would be q minus p, which is -3, right? We've done that again. And then we would do the other, and that would be 1. And then the component form for v would be 1 minus 2, which is -1, and 2 minus 3, which is -1. And you can see right away that these two vectors, when graphed in standard position with the initial point at 0, 0, and then gone, one is going to go this direction, u is going to go this direction, and then the other is going to go this direction. Obviously not equivalent. So for two vectors to be equivalent, they must have the same magnitude and direction. They might have the same magnitude, but they may be pointing in a different direction. Right? So that's a really important concept. And if you understand what you're finding when you are finding equivalent vectors, then you can use the second method and realize its significance. All right, another skill is graphing vectors, and you would think this would be pretty easy, but I have a lot of students who find this kind of confusing. So what we're doing here is I've given 1, 2, 3 different types of vectors, and we're going to add vectors and subtract vectors and multiply them times scalars, and that's kind of foreshadowing this graphing thing. But basically what happens if I have a vector that is u, vector u, and I'm going to multiply it by 3. So when I do that, multiplying it by a scalar changes its magnitude or its length. It doesn't change its direction, it changes just the length of it. So this is u, and so 3u would just be that 3 times. So it's going to change its length 3 times. Okay, the 2 on this 2v is also going to change it so that it's twice as long. V is twice as long. But this minus in front of it changes its direction. In fact, it does a 180. So in other words, instead of going that direction, it's going to be twice as long going in the opposite direction. This is -2v. Now, when you get into addition, right, addition or addition with scalar multiplication, you are changing both length and direction, right? So I'm going to take two vectors and multiply them together, or add them together. And so you can see here that u is pointing in the second quadrant, this direction, and then v is pointing in the third. Well, what I'm going to do is I'm going to use the head to tail method, or tail to head method, either way. And I'm going to take the head of v and place here at the end, or the tail of u. It's going to point in the same direction. Okay, I can kind of make a box. You see the rectangle? So u plus v is going to be this vector added together. So this is the head to tail, or sometimes they call this the parallelogram, which is hard to spell, so I usually say head to tail. Anyway, the same deal. I'm just making a parallelogram with my vectors, and I'm drawing from the initial point to this corner over here. And so this blue vector is u plus v. Right, so by the same token, if I have 3v, so I'm going to make v 3 times longer, and usually you just make it 3 times longer. And you're guessing a little bit here. I'm not measuring anything. You're just changing its magnitude, and you're trying to make it as close as possible. Well, if you use the parallelogram method, then I would just make a parallelogram, right, based on the lengths of those. And then my actual vector of those two things added together is here. So it changes both the length and the direction. And that's how you graph. It's pretty simple. And we'll do that again in class, but I find that my students have the hardest time with the graphing. So this is an introduction to vectors. If you have never seen vectors before, you will want to get into your book, read through the book, and look at the examples on top of this video. But do it now, because this introduction, as with everything we do in this class, this is the introduction, and we're going to build on this. So take really good notes, because I'm going to check them in class, and I will see you there.